In physics, the Coriolis effect is a deflection of moving objects when they are viewed in a rotating reference frame. In a reference frame with clockwise rotation, the deflection is to the left of the motion of the object. In one with counter-clockwise rotation, the deflection is to the right. Although recognized previously by others, the mathematical expression for the Coriolis force appeared in an 1835 paper by French scientist Gaspard-Gustave Coriolis, in connection with the theory of water wheels. Early in the 20th century, the term Coriolis force began to be used in connection with meteorology. Newton's laws of motion describe the motion of an object in an inertial frame of reference. When Newton's laws are transformed to a uniformly rotating frame of reference, the Coriolis and centrifugal forces appear. Both forces are proportional to the mass of the object. The Coriolis force is proportional to the rotation rate and the centrifugal force is proportional to its square. The Coriolis force acts in a direction perpendicular to the rotation axis and to the velocity of the body in the rotating frame and is proportional to the object's speed in the rotating frame. The centrifugal force acts outwards in the radial direction and is proportional to the distance of the body from the axis of the rotating frame. These additional forces are termed inertial forces, fictitious forces or pseudo forces. They allow the application of Newton's laws to a rotating system. They are correction factors that do not exist in a non-accelerating or inertial reference frame. Of course, the most commonly encountered rotating reference frame is the Earth. The Coriolis effect is caused by the rotation of the Earth and the inertia of the mass experiencing the effect. Because the Earth completes only one rotation per day, the Coriolis force is quite small, and its effects generally become noticeable only for motions occurring over large distances and long periods of time, such as large-scale movement of air in the atmosphere or water in the ocean. Such motions are constrained by the surface of the Earth, so only the horizontal component of the Coriolis force is generally important. This force causes moving objects on the surface of the Earth to be deflected in a clockwise sense in the northern hemisphere and in a counterclockwise sense in the southern hemisphere. Rather than flowing directly from areas of high pressure to low pressure, as they would in a non-rotating system, winds and currents tend to flow to the right of this direction north of the equator and to the left of this direction south of it. This effect is responsible for the rotation of large cyclones. History: Italian scientists Giovanni Battista Riccioli and his assistant Francesco Maria Grimaldi described the effect in connection with artillery in the 1651 Orma Gestum Novum, writing that rotation of the Earth should cause a cannonball fired to the north to deflect to the east. The effect was described in the tidal equations of Pierre-Simon Laplace in 1778. Gaspard-Gustave Coriolis published a paper in 1835 on the energy yield of machines with rotating parts, such as waterwheels. That paper considered the supplementary forces that are detected in a rotating frame of reference. Coriolis divided these supplementary forces into two categories. The second category contained a force that arises from the cross-product of the angular velocity of a coordinate system and the projection of a particle's velocity into a plane perpendicular to the system's axis of rotation. Coriolis referred to this force as the compound centrifugal force due to its analogies with the centrifugal force already considered in Category 1. The effect was known in the early 20th century as the acceleration of Coriolis, and by 1920 as Coriolis force. In 1856, William Ferrel proposed the existence of a circulation cell in the mid-latitudes with air being deflected by the Coriolis force to create the prevailing westerly winds. Understanding the kinematics of how exactly the rotation of the Earth affects airflow was partial at first. Late in the 19th century, the full extent of the large-scale interaction of pressure gradient force and deflecting force that in the end causes air masses to move along isobars was understood. Formula: in non-vector terms, at a given rate of rotation of the observer, the magnitude of the Coriolis acceleration of the object is proportional to the velocity of the object and also to the sine of the angle between the direction of movement of the object and the axis of rotation. The vector formula for the magnitude and direction of the Coriolis acceleration is whereas the acceleration of the particle in the rotating system is the velocity of the particle in the rotating system, and I copyright is the angular velocity vector which has magnitude equal to the rotation rate I per mil and is directed along the axis of rotation of the rotating reference frame, and the A symbol represents the cross-product operator. The equation may be multiplied by the mass of the relevant object to produce the Coriolis force. See fictitious force for a derivation. The Coriolis effect is the behavior added by the Coriolis acceleration. The formula implies that the Coriolis acceleration is perpendicular both to the direction of the velocity of the moving mass and to the frame's rotation axis. So in particular, if the velocity is parallel to the rotation axis, the Coriolis acceleration is zero. If the velocity is straight inward to the axis, the acceleration is in the direction of local rotation. If the velocity is straight outward from the axis, the acceleration is against the direction of local rotation. If the velocity is in the direction of local rotation, the acceleration is outward from the axis. If the velocity is against the direction of local rotation, the acceleration is inward to the axis. The vector cross product can be evaluated as the determinant of a matrix, where the vectors I, j, k are unit vectors in the x, y and z directions. Causes: the Coriolis effect exists only when one uses a rotating reference frame. In the rotating frame it behaves exactly like a real force. However, Coriolis force is a consequence of inertia, and is not attributable to an identifiable originating body, as is the case for electromagnetic or nuclear forces, for example. From an analytical viewpoint, to use Newton's second law in a rotating system, Coriolis force is mathematically necessary, but it disappears in a non-accelerating, inertial frame of reference. For example, consider two children on opposite sides of a spinning roundabout, who are throwing a ball to each other. From the children's point of view, this ball's path is curved sideways by the Coriolis effect. Suppose the roundabout spins counterclockwise when viewed from above. From the thrower's perspective, the deflection is to the right. From the non-thrower's perspective, deflection is to left. For a mathematical formulation, see mathematical derivation of fictitious forces. An observer in a rotating frame, such as an astronaut in a rotating space station, very probably will find the interpretation of everyday life in terms of the Coriolis force accords more simply with intuition and experience than a cerebral reinterpretation of events from an inertial standpoint. For example, nausea due to an experienced push may be more instinctively explained by Coriolis force than by the law of inertia. See also Coriolis effect. In meteorology, a rotating frame with its Coriolis force proves a more natural framework for explanation of air movements than a non-rotating, inertial frame without Coriolis forces. In long-range gunnery, sight corrections for the Earth's rotation are based upon Coriolis force. These examples are described in more detail below. The acceleration entering the Coriolis force arises from two sources of change in velocity that result from rotation. The first is the change of the velocity of an object in time. The same velocity will be seen as different velocities at different times in a rotating frame of reference. The apparent acceleration is proportional to the angular velocity of the reference frame, and to the component of velocity of the object in a plane perpendicular to the axis of rotation. This gives a term. The minus sign arises from the traditional definition of the cross product, and from the sign convention for angular velocity vectors. The second is the change of velocity in space. Different positions in a rotating frame of reference have different velocities. In order for an object to move in a straight line, it must therefore be accelerated so that its velocity changes from point to point by the same amount as the velocities of the frame of reference. The effect is proportional to the angular velocity, and to the component of the velocity of the object in a plane perpendicular to the axis of rotation. This also gives a term. Length scales and the Rossby number. The time, space and velocity scales are important in determining the importance of the Coriolis effect. Whether rotation is important in a system can be determined by its Rossby number, which is the ratio of the velocity, u, of a system to the product of the Coriolis parameter and the length scale, L, of the motion. The Rossby number is the ratio of inertial to Coriolis forces. A small Rossby number signifies a system which is strongly affected by Coriolis forces, and a large Rossby number signifies a system in which inertial forces dominate. For example, in tornadoes, the Rossby number is large, in low-pressure systems it is low, and in oceanic systems it is around 1. As a result, in tornadoes the Coriolis force is negligible, and balances between pressure and centrifugal forces. In low-pressure systems, centrifugal force is negligible and balances between Coriolis and pressure forces. In the oceans all three forces are comparable. An atmospheric system moving at w equals a 10 ams occupying a spatial distance of l equals a 1000 km, has a Rossby number of approximately 0.1. A baseball pitcher may throw the ball at w equals a 45 ams for a distance of l equals a 18.3 am. The Rossby number in this case would be 32,000. Needless to say, one does not worry about which hemisphere one is in when playing baseball. However, an unguided missile obeys exactly the same physics as a baseball, but may travel far enough and be in the air long enough to notice the effect of Coriolis. Long-range shells in the northern hemisphere landed close to, but to the right of, where they were aimed until this was noted. In fact, it was this effect that first got the attention of Coriolis himself. Applied to Earth, an important case where the Coriolis force is observed is the rotating Earth. Unless otherwise stated, directions of forces and motion apply to the northern hemisphere. Intuitive explanation: as the Earth turns around its axis, everything attached to it turns with it. An object that is moving without being dragged along with this rotation travels in a straight motion over the turning Earth. From our rotating perspective on the planet, its direction of motion changes as it moves, bending in the opposite direction to our actual motion. When viewed from a stationary point in space above, any land feature in the northern hemisphere turns counterclockwise, and, fixing our gaze on that location, any other location in that hemisphere will rotate around it the same way. The traced ground path of a freely moving body traveling from one point to another will therefore bend the opposite way, clockwise, which is conventionally labeled as right, where it will be if the direction of motion is considered ahead, and down is defined naturally. Rotating sphere. Consider a location with latitude I on a sphere that is rotating around the north-south axis. A local coordinate system is set up with the x-axis horizontally due east, the y-axis horizontally due north and the z-axis vertically upwards. The rotation vector, velocity of movement and Coriolis acceleration expressed in this local coordinate system, north and upward, are, a. When considering atmospheric or oceanic dynamics, the vertical velocity is small, and the vertical component of the Coriolis acceleration is small compared to gravity. For such cases, only the horizontal components matter. The restriction of the above to the horizontal plane is, a, where is called the Coriolis parameter. By setting Vn equals 0, it can be seen immediately that a movement due east results in an acceleration due south. Similarly, setting V equals 0, it is seen that a movement due north results in an acceleration due east. In general, observed horizontally, looking along the direction of the movement causing the acceleration always is turned 90 degrees to the right and of the same size regardless of the horizontal orientation. As a different case, consider equatorial motion setting I equals 0 degree. In this case, I copyright is parallel to the north or n-axis, and, accordingly, an eastward motion provides an upward acceleration known as the A paragraph S effect, and an upward motion produces an acceleration due west. Distant stars. The apparent motion of a distant star as seen from Earth is dominated by the Coriolis and centrifugal forces. Consider such a star located at position R, with declination I, so I copyright a Rankine equals a I copyright sin, I, where I copyright is the Earth's rotation vector. The star is observed to rotate about the Earth's axis with a period of one sidereal day in the opposite direction to that of the Earth's rotation, making its velocity v equals a I copyright a, r. The fictitious force, consisting of Coriolis and centrifugal forces, is where E copyright equals IV1. I copyright is a unit vector in the direction of I copyright. The fictitious force FF is thus a vector of magnitude ma I copyright 2 a cos, I, perpendicular to I copyright, and directed towards the center of the star's rotation on the Earth's axis, and therefore recognizable as the centripetal force that will keep the star in a circular movement around that axis. Meteorology. Perhaps the most important impact of the Coriolis effect is in the large-scale dynamics of the oceans and the atmosphere. In meteorology and oceanography, it is convenient to postulate a rotating frame of reference wherein the Earth is stationary. In accommodation of that provisional postulation, the centrifugal and Coriolis forces are introduced. Their relative importance is determined by the applicable Rossby numbers. Tornadoes have high Rossby numbers, so, while tornado-associated centrifugal forces are quite substantial, Coriolis forces associated with tornadoes are for practical purposes negligible. Because currents are driven by the movement of wind across the water of the ocean, the Coriolis effect also affects the movement of the ocean. Unregistered trademark S currents and therefore hurricanes as well. Many of the ocean's largest currents circulate around warm, high-pressure areas called gyres. Though the circulation is not as significant as that in the air, the deflection caused by the Coriolis effect is what creates the spiraling pattern in these gyres. The spiraling wind pattern helps the hurricane form. The stronger the force from the Coriolis effect, the faster the wind will spin and pick up additional energy, increasing the strength of the hurricane. Air within high-pressure systems rotates in a direction such that the Coriolis force will be directed radially inwards, and nearly balanced by the outwardly radial pressure gradient. As a result, air travels clockwise around high pressure in the northern hemisphere and counterclockwise in the southern hemisphere. Air within low-pressure systems rotates in the opposite direction, so that the Coriolis force is directed radially outward and nearly balances an inwardly radial pressure gradient. Flow around a low-pressure area. If a low-pressure area forms in the atmosphere, air will tend to flow in towards it, but will be deflected perpendicular to its velocity by the Coriolis force. A system of equilibrium can then establish itself, creating circular movement, or a cyclonic flow. Because the Rossby number is low, the force balance is largely between the pressure gradient force acting towards the low pressure area and the Coriolis force acting away from the center of the low pressure. Instead of flowing down the gradient, large-scale motions in the atmosphere and ocean tend to occur perpendicular to the pressure gradient. This is known as geostrophic flow. On a non-rotating planet, fluid would flow along the straightest possible line, quickly eliminating pressure gradients. Note that the geostrophic balance is thus very different from the case of inertial motions, which explains why mid-latitude cyclones are larger by an order of magnitude than inertial circle flow would be. This pattern of deflection, and the direction of movement, is called Buys-Ballott's law. In the atmosphere, the pattern of flow is called a cyclone. In the northern hemisphere, the direction of movement around a low-pressure area is counterclockwise. In the southern hemisphere, the direction of movement is clockwise because the rotational dynamics is a mirror image there. At high altitudes, outward spreading air rotates in the opposite direction. Cyclones rarely form along the equator due to the weak Coriolis effect present in this region. Inertial circles, an air or water mass moving with speed subject only to the Coriolis force, travels in a circular trajectory called an inertial circle. Since the force is directed at right angles to the motion of the particle, it will move with a constant speed around a circle whose radius is given by. Where is the Coriolis parameter, introduced above? The time taken for the mass to complete a full circle is therefore. The Coriolis parameter typically has a mid-latitude value of about 10^4 r1. Hence, for a typical atmospheric speed of 10 ams, the radius is 100 km, with a period of about 17 hours. For an ocean current with a typical speed of 10 cm per second, the radius of an inertial circle is 1 km. These inertial circles are clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. If the rotating system is a parabolic turntable, then is constant and the trajectories are exact circles. On a rotating planet, varies with latitude and the paths of particles do not form exact circles. Since the parameter varies as the sign of the latitude, the radius of the oscillations associated with a given speed are smallest at the poles, and increase toward the equator. Other terrestrial effects, the Coriolis effect strongly affects the large-scale oceanic and atmospheric circulation, leading to the formation of robust features like jet streams and western boundary currents. Such features are in geostrophic balance, meaning that the Coriolis and pressure gradient forces balance each other. Coriolis acceleration is also responsible for the propagation of many types of waves in the ocean and atmosphere, including Rossby waves and Kelvin waves. It is also instrumental in the so-called Ekman dynamics in the ocean, and in the establishment of the large-scale ocean flow pattern called the Sverdrup balance. A paragraph Chvar paragraph S effect. The practical impact of the Coriolis effect is mostly caused by the horizontal acceleration component produced by horizontal motion. There are other components of the Coriolis effect. Eastward traveling objects will be deflected upwards, while westward traveling objects will be deflected downwards. This is known as the A paragraph Chvar paragraph S effect. This aspect of the Coriolis effect is greatest near the equator. The force produced by this effect is similar to the horizontal component, but the much larger vertical forces due to gravity and pressure mean that it is generally unimportant dynamically. In addition, objects traveling upwards or downwards will be deflected to the west or east respectively. This effect is also the greatest near the equator. Since vertical movement is usually of limited extent and duration, the size of the effect is smaller and requires precise instruments to detect. However, in the case of large changes of momentum, such as a spacecraft being launched into orbit, the effect becomes significant. The fastest and most fuel-efficient path to orbit is a launch from the equator which curves to a directly eastward heading. Draining in bathtubs and toilets. Contrary to popular misconception, water rotation in home bathrooms under normal circumstances is not related to the Coriolis effect or to the rotation of the Earth, and no consistent difference in rotation direction between toilets in the northern and southern hemispheres can be observed. The formation of a vortex over the plug hole may be explained by the conservation of angular momentum. The radius of rotation decreases as water approaches the plug hole, so the rate of rotation increases, for the same reason that an ice skater's rate of spin increases as they pull their arms in. Any rotation around the plug hole that is initially present accelerates as water moves inward. Only if the water is so still that the effective rotation rate of the Earth is faster than that of the water relative to its container, and if externally applied torques are small enough, the Coriolis effect may determine the direction of the vortex. Without such careful preparation, the Coriolis effect may be much smaller than various other influences on drain direction such as any residual rotation of the water and the geometry of the container. Despite this, the idea that toilets and bathtubs drain differently in the northern and southern hemispheres has been popularized by several television programs and films, including Escape Plan, Wedding Crashers, The Simpsons episode Bart vs. Australia, and The X-Files episode Die Hand Die Verletzt. Several science broadcasts and publications, including at least one college-level physics textbook, have also stated this. In 1908, the Austrian physicist Ottokar Termleitz described careful and effective experiments which demonstrated the effect of the rotation of the Earth on the outflow of water through a central aperture. The subject was later popularized in a famous article in the journal Nature, which described an experiment in which all other forces to the system were removed by filling a 6 LFT tank with 300 US a gal of water and allowing it to settle for 24 hours, in a room where the temperature had stabilized. The drain plug was then very slowly removed, and tiny pieces of floating wood were used to observe rotation. During the first 12 to 15 minutes, no rotation was observed. Then, a vortex appeared and consistently began to rotate in a counter-clockwise direction. This was repeated and the results averaged to make sure the effect was real. The report noted that the vortex rotated, about 30,000 times faster than the effective rotation of the Earth in 42° north. This shows that the small initial rotation due to the Earth is amplified by gravitational draining and conservation of angular momentum to become a rapid vortex and may be observed under carefully controlled laboratory conditions. Ballistic missiles and satellites. Ballistic missiles and satellites appear to follow curved paths when plotted on common world maps, mainly because the Earth is spherical and the shortest distance between 2 points on the Earth's surface is usually not a straight line on those maps. Every two-dimensional map necessarily distorts the Earth's curved surface. Typically, this distortion increases with proximity to the poles. In the Northern Hemisphere, for example, a ballistic missile fired toward a distant target using the shortest possible route will appear on such maps to follow a path north of the straight line from target to destination, and then curve back toward the equator. This occurs because the latitudes, which are projected as straight horizontal lines on most world maps, are in fact circles on the surface of a sphere, which gets smaller as they get closer to the pole. Being simply a consequence of the sphericity of the Earth, this would be true even if the Earth didn't rotate. The Coriolis effect is of course also present, but its effect on the plotted path is much smaller. The Coriolis effects became important in external ballistics for calculating the trajectories of very long-range artillery shells. The most famous historical example was the Paris gun, used by the Germans during World War I to bombard Paris from a range of about 120 km. Special cases, cannon on turntable. The animation at the top of this article is a classic illustration of Coriolis Force. Another visualization of the Coriolis and centrifugal forces is this animation clip. Given the radius r of the turntable in that animation, the rate of angular rotation I per mil, and the speed of the cannonball v, the correct angle I to aim so as to hit the target at the edge of the turntable can be calculated. The inertial frame of reference provides one way to handle the question: calculate the time to interception, which is Tf equals a/v. Then, the turntable revolves an angle I per mil Tf in this time. If the cannon is pointed an angle I equals I per mil Tf equals I per mil a/v, then the cannonball arrives at the periphery at position number 3 at the same time as the target. No discussion of Coriolis force can arrive at this solution as simply, so the reason to treat this problem is to demonstrate Coriolis formalism in an easily visualized situation. The trajectory in the inertial frame is a straight line radial path at angle I. The position of the cannonball in coordinates at time t is. In the turntable frame, the xy axis rotate at angular rate I per mil, so the trajectory becomes. And 3 examples of this result are plotted in the figure. To determine the components of acceleration, a general expression is used from the article fictitious force, a euro, in which the term in I copyright A, VB is the Coriolis acceleration and the term in I copyright A, is the centrifugal acceleration. The results are, a euro, producing a centrifugal acceleration, a euro, also, a euro, a euro, producing a Coriolis acceleration, a euro. These accelerations are shown in the diagrams for a particular example. It is seen that the Coriolis acceleration not only cancels the centrifugal acceleration, but together they provide a net centripetal, radially inward component of acceleration, and an additional component of acceleration perpendicular to RB, a euro. The centripetal component of acceleration resembles that for circular motion at radius RB, while the perpendicular component is velocity dependent, increasing with the radial velocity v and directed to the right of the velocity. The situation could be described as a circular motion combined with an apparent Coriolis acceleration of 2I per mil v. However, this is a rough labeling. A careful designation of the true centripetal force refers to a local reference frame that employs the directions normal and tangential to the path, not coordinates referred to the axis of rotation. These results also can be obtained directly by two-time differentiations of RB. Agreement of the two approaches demonstrates that one could start from the general expression for fictitious acceleration above and derive the trajectories shown here. However, working from the acceleration to the trajectory is more complicated than the reverse procedure used here, which, of course, is made possible in this example by knowing the answer in advance. As a result of this analysis, an important point appears: all the fictitious accelerations must be included to obtain the correct trajectory. In particular, besides the Coriolis acceleration, the centrifugal force plays an essential role. It is easy to get the impression from verbal discussions of the cannonball problem, which are focused on displaying the Coriolis effect particularly, that the Coriolis force is the only factor that must be considered. Emphatically, that is not so. A turntable for which the Coriolis force is the only factor is the parabolic turntable. A somewhat more complex situation is the idealized example of flight routes over long distances, where the centrifugal force of the path and aeronautical lift are countered by gravitational attraction. Tossed ball on a rotating carousel. A figure illustrates a ball tossed from 12:00 o'clock toward the center of a counterclockwise rotating carousel. On the left, the ball is seen by a stationary observer above the carousel, and the ball travels in a straight line to the center, while the ball thrower rotates counterclockwise with the carousel. On the right, the ball is seen by an observer rotating with the carousel, so the ball thrower appears to stay at 12:00. The figure shows how the trajectory of the ball as seen by the rotating observer can be constructed. On the left, two arrows locate the ball relative to the ball thrower. One of these arrows is from the thrower to the center of the carousel, and the other points from the center of the carousel to the ball. This arrow gets shorter as the ball approaches the center. A shifted version of the two arrows is shown dotted. On the right is shown this same dotted pair of arrows, but now the pair are rigidly rotated so the arrow corresponding to the line of sight of the ball thrower toward the center of the carousel is aligned with 12:00. The other arrow of the pair locates the ball relative to the center of the carousel, providing the position of the ball as seen by the rotating observer. By following this procedure for several positions, the trajectory in the rotating frame of reference is established as shown by the curved path in the right-hand panel. The ball travels in the air, and there is no net force upon it. To the stationary observer, the ball follows a straight line path, so there is no problem squaring this trajectory with zero net force. However, the rotating observer sees a curved path. Kinematics insists that a force must be present to cause this curvature, so the rotating observer is forced to invoke a combination of centrifugal and Coriolis forces to provide the net force required to cause the curved trajectory. Bounced ball. A figure describes a more complex situation where the tossed ball on a turntable bounces off the edge of the carousel and then returns to the tosser, who catches the ball. The effect of Coriolis force on its trajectory is shown again as seen by two observers, an observer that rotates with the carousel, and an inertial observer. The figure shows a bird's-eye view based upon the same ball speed on forward and return paths. Within each circle, plotted dots show the same time points. In the left panel, from the camera's viewpoint at the center of rotation, the tosser and the rail both are at fixed locations, and the ball makes a very considerable arc on its travel toward the rail, and takes a more direct route on the way back. From the ball tosser's viewpoint, the ball seems to return more quickly than it went. On the carousel, instead of tossing the ball straight at a rail to bounce back, the tosser must throw the ball toward the right of the target, and the ball then seems to the camera to bear continuously to the left of its direction of travel to hit the rail. The ball appears to bear to the left from direction of travel on both inward and return trajectories. The curved path demands this observer to recognize a leftward net force on the ball. For some angles of launch, a path has portions where the trajectory is approximately radial, and Coriolis force is primarily responsible for the apparent deflection of the ball. When a path curves away from radial, however, centrifugal force contributes significantly to deflection. The ball's path through the air is straight when viewed by observers standing on the ground. In the right panel, the ball tosser is at 12:00 and the rail the ball bounces from is at position 1. From the inertial viewer's standpoint, positions 1, 2, 3 are occupied in sequence. At position 2 the ball strikes the rail, and at position 3 the ball returns to the tosser. Straight-line paths are followed because the ball is in free flight, so this observer requires that no net force is applied. Bullets at high velocity through the atmosphere, because of the rotation of the Earth, a bullet does not fly straight from the barrel to a target. The Coriolis effect minutely changes the trajectory of a bullet, curving the path of the projectile into a more arched semicircle shape. This effect only affects accuracy at extremely long distances and is therefore accounted for by accurate long-distance shooters, such as snipers and other trained professionals. Visualization of the Coriolis effect. To demonstrate the Coriolis effect, a parabolic turntable can be used. On a flat turntable, the inertia of a co-rotating object would force it off the edge. But if the surface of the turntable has the correct paraboloid shape and is rotated at the corresponding rate, the force components shown in the figure are such that the component of gravity tangential to the bowl surface will exactly equal the centripetal force necessary to keep the object rotating at its velocity and radius of curvature. This carefully contoured surface allows the Coriolis force to be displayed in isolation. Discs cut from cylinders of dry ice can be used as pucks, moving around almost frictionlessly over the surface of the parabolic turntable, allowing effects of Coriolis on dynamic phenomena to show themselves. To get a view of the motions as seen from the reference frame rotating with the turntable, a video camera is attached to the turntable so as to co-rotate with the turntable, with results as shown in the figure. In the left panel of the figure, which is the viewpoint of a stationary observer, the gravitational force in the inertial frame pulling the object toward the center of the dish is proportional to the distance of the object from the center. A centripetal force of this form causes the elliptical motion. In the right panel, which shows the viewpoint of the rotating frame, the inward gravitational force in the rotating frame is balanced by the outward centrifugal force. With these two forces balanced, in the rotating frame the only unbalanced force is Coriolis, and the motion is an inertial circle. Analysis and observation of circular motion in the rotating frame is a simplification compared to analysis or observation of elliptical motion in the inertial frame. Because this reference frame rotates several times a minute rather than only once a day like the Earth, the Coriolis acceleration produced is many times larger and so easier to observe on small time and spatial scales than is the Coriolis acceleration caused by the rotation of the Earth. In a manner of speaking, the Earth is analogous to such a turntable. The rotation has caused the planet to settle on a spheroid shape, such that the normal force, the gravitational force and the centrifugal force exactly balance each other on a horizontal surface. The Coriolis effect caused by the rotation of the Earth can be seen indirectly through the motion of a Foucault pendulum. Coriolis effects in other areas. Coriolis Flowmeter. A practical application of the Coriolis effect is the mass flow meter, an instrument that measures the mass flow rate and density of a fluid flowing through a tube. The operating principle involves inducing a vibration of the tube through which the fluid passes. The vibration, though it is not completely circular, provides the rotating reference frame which gives rise to the Coriolis effect. While specific methods vary according to the design of the flow meter, sensors monitor and analyze changes in frequency, phase shift, and amplitude of the vibrating flow tubes. The changes observed represent the mass flow rate and density of the fluid. Molecular physics. In polyatomic molecules, the molecule motion can be described by a rigid body rotation and internal vibration of atoms about their equilibrium position. As a result of the vibrations of the atoms are in motion relative to the rotating coordinate system of the molecule. Coriolis effects will therefore be present and will cause the atoms to move in a direction perpendicular to the original oscillations. This leads to a mixing in molecular spectra between the rotational and vibrational levels from which Coriolis coupling constants can be determined. Insect flight. Flies and moths utilize the Coriolis effect when flying. Their halters, or antennae in the case of moths, oscillate rapidly and are used as vibrational gyroscopes. See Coriolis effect in insect stability. In this context, the Coriolis effect has nothing to do with the rotation of the Earth. See also. References. Further reading, Physics and Meteorology. Historical. External links, the definition of the Coriolis effect from the Glossary of Meteorology. The Coriolis effect a conflict between common sense and mathematics PDF file. 20 pages. a general discussion by Anders Persson of various aspects of the Coriolis effect, including Foucault's pendulum and Taylor columns. Anders Persson. The Coriolis effect, 4 centuries of conflict between common sense and mathematics, Part 1, A History to 1885. History of Meteorology 2, 10 Coriolis effect videos and games from the About.com weather page, Coriolis Force from Science World, Coriolis Effect and Rains. An article from the Newton website hosted by the Argonne National Laboratory. Catalogue of Coriolis videos, Coriolis Effect, a graphical animation, a visual earth animation with precise explanation, an introduction to fluid dynamics. SpinLab educational film explains the Coriolis effect with the aid of lab experiments. Do bathtubs drain counterclockwise in the Northern Hemisphere? By Cecil Adams. Bad Coriolis. An article uncovering misinformation about the Coriolis effect. By Alistair B. Fraser, Emeritus Professor of Meteorology at Pennsylvania State University, The Coriolis Effect, a simple explanation, an explanation for the layperson. Observe an animation of the Coriolis effect over Earth's surface, animation clip showing scenes as viewed from both an inertial frame and a rotating frame of reference, visualizing the Coriolis and centrifugal forces. Vincent Millet. The Coriolis Force at INWIT, NASA notes, interactive Coriolis fountain lets you control rotation speed, droplet speed and frame of reference to explore the Coriolis effect. Nigir on Schools Online. The Coriolis effect,